Okay, so in this movie, I'm going to provide a brief introduction to molecular orbital theory to help support the reading from your textbook. So what is molecular orbital theory and what is a molecular orbital? Well, molecular orbital theory is a bonding theory which helps us to understand why atoms come together to form stable bonds. In other words, why do atoms combine to form molecules? And if you recall from your earlier discussions of covalent bonding, electrons in covalent molecules are shared between the nuclei of the atoms in the molecule. So the molecular orbital describes the electron density for those shared electrons that are surrounding the entire molecule. So it's a description of the probability density of the electrons in the molecule. So just as atomic orbitals showed the probability density for electrons around atoms, in molecules, since the electrons are shared among all the atoms, the molecular orbital describes how those electrons are arranged around the entire molecule. So for example, in H2, the lowest energy orbital is shown here. The gray represents the 90% probability region of finding the electrons in the H2 molecule. And of course it covers the entire molecule because the electrons are shared between the two H atoms. The nuclei are represented by the dots here. So you may recall Schrödinger came up with a wave description of the electron. He had a mathematical description of the electron wave. In its simplest formulation, it's H psi is equal to E psi. And in this mathematical model, psi is the wave description of the electron, and E is the energy. In addition, psi squared provides our physical understanding of the electron. It is the probability density of the electron in a region of space. So Schrödinger was able to develop a mathematical model for the electron which produced its wave description, its energy, and then psi, the square of that function, which gives us our physical relevance to the electron, sort of where it is in the region of space around the atom, or in this case the molecule. Okay, so solving the Schrödinger equation for the H atom, as you may recall, produces the various atomic orbitals, s, p, d, and so forth, along with their energies. So when you solve H psi is equal to E psi, you're able to produce these s, p, and d orbitals, which are essentially psi squared. And we've plotted those before, like this. Right? So we have the various orbitals of the atom arranged in increasing energy, and of course these go on, s and d and so forth, s, d, p, and so forth. Solving the Schrödinger equation for the H2 plus, which is the simplest diatomic molecule, produces the various molecular orbitals. So in this case, right, if we apply the equation for molecules like H2, we get descriptions of the molecular orbitals which look like this. So these molecular orbitals probably look fairly complex, and they are, but we will find that we can produce them relatively easily by thinking of them as combinations of the original atomic orbitals on the atoms that are bonded together. So in other words, we can take combinations of the atomic orbitals, like the s orbitals on the H atom, and combine them to make molecular orbitals. So for instance, imagine two hydrogen atoms that are separated in space like this. And if we solve the Schrodinger equation to produce the atomic orbitals, right, they would be separated just like this, and each would have its own energy associated with it. However, if you place the nuclei closer together, right, so we're starting here with the two separate atoms with a particular energy, right, not bonded, and then we show them closer together at a separation distance b, and then solve the Schrodinger equation for these two nuclei closer together, we get a new combined orbital with an energy shown here. So this is the separation distance, right? And that's the energy you would get. And as you keep bringing the nuclei closer together, the energy decreases. And so we're seeing, as we go down, placing the nuclei closer together and then solve the Schrodinger equation for the orbital, we get a lower and lower energy orbital until a certain separation distance in which the energy is at its lowest. And that will be the ground state molecular orbital for the hydrogen atom. If we place the nuclei even closer together, shown here, then the energy goes back up due to repulsive forces between the positively charged nuclei being too close together. So you can see here we started with two separate H atoms and their atomic orbitals, and eventually combined them to produce the ground state molecular orbital, which is shown right here at the lowest energy. And so molecular orbitals can be thought of as combinations of atomic orbitals.